Get ready to embark on an epic game development journey and recreate the most popular game ever created, Tetris. With just a few hours of your time, you'll be able to create your very own fully functional and engaging Tetris game using the C++ programming language and the raylib library. Join me as I take you step by step through the process, from setting up the game loop to creating the game grid and blocks, to implementing movement, collision detection, and scoring. You will learn invaluable game development concepts and techniques along the way. And by the end of this tutorial, you'll have a polished and exciting Tetris game that you can proudly share with the world. To make sure you don't miss out on any updates and new tutorials, be sure to subscribe to my channel and hit that like button to show your support. So, what are you waiting for? Let's dive into the world of Tetris game development together. Subscribe now and let's get started. But why build Tetris on your own if tools like ChatGPT can build it for you in seconds? In today's world of constant distractions, shortened attention spans, and easy access to AI tools, it is more important than ever to develop the ability to focus on a complex task and see it through to completion. Building a game like Tetris from scratch will challenge you to break down a complex problem into manageable steps, strengthen your problem-solving skills, and improve your ability to concentrate on a project from start to finish. Today, there are so many distractions vying for our attention, from social media notifications to instant messaging, that it can be difficult to concentrate on any one task for an extended period of time. However, the ability to concentrate is crucial for success in any field, including game development. Without focus, it is easy to become overwhelmed by the complexity of a project like Tetris and give up before completing it. As my favorite thinker Charlie Munger said, I succeeded because I have a long attention span. Google Charlie Munger to see how successful he is and what he has accomplished. Long attention span and focus lead to success. Not to mention the satisfaction that comes with creating something entirely from your own ideas and hard work. I promise you, if you complete this tutorial, you are going to feel very happy. Trust me. Also, learning to build a Tetris game using C++ and raylib is a great way to improve your coding skills and expand your knowledge of game development. By following this tutorial, you'll be able to learn the fundamentals of C++ programming, such as loops, conditionals, functions, and object-oriented programming. You'll also gain experience with raylib, a powerful library for building 2D games in C++. In order to follow this tutorial, I expect you to have a basic knowledge of the C++ programming language and a development environment for C++ already installed. I am going to work with Visual Studio Code. Lastly, we are going to need the raylib library. I have prepared a detailed video on how to install raylib on your Windows computer and use it with Visual Studio Code. You can watch it here. It will help you set up everything on your Windows computer. If you prefer to use Visual Studio, check out the second tutorial I have prepared. It will be linked in the video description as well. If you use a different operating system, you can still follow this tutorial if you have a working C++ setup with the raylib library. Additionally, if you are new to game development with raylib, I suggest starting out with our Pong and Snake game tutorials, also linked in the video description, to make the learning process smoother. Don't worry if you are not yet an expert in C++. This tutorial will provide valuable insights and help you learn a lot. So, if you have set up everything and you can compile and run a simple raylib example program, we are ready to go. As Lao Tse once said, the journey of 1,000 miles begins with a single step. So, let's take that first step towards creating our own Tetris game and see where this journey takes us. Tetris may seem complex and challenging to develop, but fear not. We will take a divide and conquer approach to make it more manageable. In this tutorial, we will break the development process down into 12 steps. tackling each one individually and building upon what we have accomplished in previous steps. With this approach, you'll be well on your way to creating your own Tetris game in no time. So let's get started and see how we can conquer this challenging project one step at a time. The first step in building our Tetris game is to create a blank screen and set up the game loop. Before we start, it is important to understand the structure of a game. Every game consists of two parts: the part where we define our variables and game objects, such as the grid, the blocks, and the user interface, and the game loop, which is responsible for updating the positions of the game objects and checking for collisions. The game loop is like the heartbeat of the game, running repeatedly until the game is closed. In each iteration of the game loop, we will draw the game objects in their new positions and check for collisions, all happening so fast that it appears as a continuous movement. Now, let's create a blank screen and the game loop. Let's open the C++ starter template for raylib that I have created with VS Code. You can download this template project by visiting this GitHub repository. If you open this template with Visual Studio Code, you can see it is organized in folders. We have to open the source folder and double-click on the main.cpp file. If we now compile and run this project by pressing F5 on the keyboard, it displays a bouncing ball example. Cool, our setup works. We are ready to start developing our game. Let's delete the ball.h and ball.cpp files and all the code from the main.cpp file. Just leave the include raylib line and the main function just like I did. Now let's create a blank screen for our game and the game loop. First of all, we have to create our game window. The game window is like a black canvas where we can draw our game objects. We need to specify the width and the height of the game window. I am going to use a size of 300 by 600 pixels for now. We will change that later. To create the game window, we have to call the initWindow function. This function initializes a window and takes three arguments: the width and the height of the window and the title. For the width and the height, let's enter 300 by 600, and for the title of the window, let's enter raylib Tetris. Now, every time we create a window, at some point we have to destroy it, and we do so with the close window function. So, let's add the close window function here. We just created a game window, and to draw in it, we use a coordinate system similar to the one taught in high school. Each point on this window has its unique x and y values. The coordinate system used in computer graphics differs from the standard Cartesian coordinate system taught in high school. In computer graphics, the origin of the display is located at the top left corner, with 0, 0 being at the top left. In contrast, the standard Cartesian coordinate system starts from the bottom left corner, with 0, 0 being the origin. In this system, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move up. However, in the top left corner coordinate system used in computer graphics, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move down. This means that a point at 10, 10 will be located 10 units to the right and 10 units down from the origin. We will be using the top left corner coordinate system in our Tetris game. That's why it is important to understand the differences between these two coordinate systems. The basic setup of the game is ready. Let's now work on the game loop. The game loop consists of three parts: event handling. First, we need to check for any events that occur in the game, such as quitting the game, a key pressed on the keyboard, etc. Updating positions. Next, we update the positions of all the game objects, such as the block, based on the events we detected in step number 1. Drawing objects. Finally, we draw all the game objects in their new positions on the screen. This step uses the raylib graphics functions to render the objects on the display. By following these three steps, we can create a dynamic and interactive game that responds to the user inputs and updates its state accordingly. We start the game loop with a while loop like this. While parentheses, and curly brackets. The while loop will run over and over again until we close the game. The first thing we do inside the game loop is to check for any events. Now, inside the parentheses, we type the condition. Window should close, parentheses, equals false. The window should close raylib function is a very useful function. It checks if the escape key on the keyboard is pressed or if the close icon of the window is pressed and returns true if that is the case. So if it returns true, the game loop ends and the window is destroyed. Our game loop needs two more functions. First, we need to call the begin drawing function. This function creates a blank canvas so we can draw our game objects on. Next, we need to call the end drawing function, which ends the canvas drawing. Lastly, there is something else we need to do. We have to define how fast the game should run. We do so by calling the setTargetFPS function before the game loop. The setTargetFPS function takes an integer as an argument, and that integer is the number of frames per second that we want. I am going to use 60 frames per second. setTargetFPS 60. That's it. If we don't define a frame rate for our game, the computer will try to run the game as fast as it can, so the game speed will depend on the speed of the computer. By defining a frame rate, we make sure that the game runs at the same speed on every computer. For this game, we define that we want to run this while loop and update the display 60 times per second. Now that the game loop is complete, we can run the game for the first time. If we run the game at this point, we won't see anything inside the game window because we haven't drawn anything yet. But the important thing is that we can see the game window with the title and the dimensions we defined, and that we can reliably close the game by clicking on this X icon here or the escape button on the keyboard. Cool, but the game window is black. Let's give it a dark blue color. Raylib provides several built-in colors, but we will be defining our own colors for this game. In Raylib, colors are represented using a struct called color, which contains 4 unsigned byte components: red, green, blue, and alpha. The values for each component range from 0 to 255, where 0 represents the absence of the color and 255 represents the full intensity of the color. For example, to create a red color, you will create a color struct with the following values. Color red equals to, curly brackets, 255, 0, 0, 255. The first 3 values represent the red, green, and blue components respectively, while the fourth value represents the alpha component, or the transparency of the color. In this case, the alpha value is set to 255, which means the color is completely opaque. So, to create a dark blue color, we will create a color struct like this. Color dark blue is equal to curly brackets 44, 44, 127, 255. Inside the game loop, before the end drawing function, we call the clear background function. Clear background, parenthesis, dark blue. So when the clear background function is called, the Windows background is cleared with this blue color. This is typically done at the start of each frame of the game loop, so that the previous frame's graphics are wiped clean and that the new frame can be drawn without any old artifacts or remnants. If we run the game now, we can see the game window is now dark blue. Beautiful. We just completed a very basic game loop, so we can remove step number 1 from our list. We have made progress. Let's now work on step number 2. To prepare for writing code, it is important to take a step back and think through the game logic thoroughly. In Tetris, the gameplay area is a grid consisting of 20 rows and 10 columns. The game pieces, or tetrominos, fall down the grid and the player must arrange them to form complete rows without any gaps. We will count the rows from the top to the bottom and the columns from left to right, with the top left cell at row 0 and column 0 being the origin. To represent the grid, we will use a two-dimensional array. In our implementation, empty cells will be represented by the value 0. When a tetromino, a block, is permanently placed on the grid by the player, the corresponding cells will be assigned a value reflecting its color. For example, if we place a red tetromino on the grid, we will assign the value 2 to the cells it covers. Similarly, if we place a yellow block, we will assign the value 4 to its corresponding cells. Each color has a unique numerical value, and since there are 7 different colors in the game, the values used in the 2D array will range from 0 to 7. 0 for an empty cell and 1 to 7 for the colors of the blocks. So if the game state at some point is something like this, the two-dimensional array will look like this. However, the current block that can still be controlled by the player will not be reflected in the array and will instead be stored and managed separately in the game logic. Now that we have a clear understanding of the game grid, we can begin implementing it in code. Let's go back to our code. We are going to use object-oriented programming to help us organize our code. We will create a grid class. As we are creating a separate class for our game grid, we need to separate the declaration of the class and its implementation. This is where the header file and the implementation file come into play. The header file, usually with a .h extension, contains the class declaration, including the class name, member variables, and function prototypes. It serves as an interface for other parts of the program to use the class. On the other hand, the implementation file, usually with a .cpp extension, contains the actual implementation of the class functions. This is where the member functions defined in the header file are implemented. Separating the class declaration from its implementation allows for better organization and abstraction of code, making it easier to manage and maintain large projects. So we will need to create 2 new files to create the grid class. I press Ctrl+N to create a new file and then Ctrl+S to save it as grid.h. Now we can start writing the header file of our grid class. Sharp pragma once. This is an instruction that ensures that this header file is only included once in a compilation unit to avoid duplicate definitions. Now we can define our class. Class, grid, curly brackets, and a semicolon. Our class will have some public and some private methods. So let's add public colon here and private colon here. Now the first public method is going to be a constructor. So we type grid, parentheses, and a semicolon here. Now, what do we want to know about the grid? First, we need to know how many rows and how many columns it contains. So let's create 2 attributes to store this information. Do the other parts of our game need to know how many rows and columns the grid has? Probably not. So let's declare these attributes as private. Int num rows, int num columns. Next, we need to know the size of each cell of the grid in pixels. Int cell size. Now we need a 2-dimensional array to represent the grid itself. Let's make this attribute public for now because we're going to need to modify the grid for testing. Int grid brackets 20 brackets 10. We declare an int array with 20 rows and 10 columns. Now let's work on the implementation of the grid class. Let's create a new file, Ctrl+N, and then Ctrl+S, and we name it grid.cpp. The first thing we have to do is to include the header file we created a few minutes ago. Include grid.h. Now we need to implement the constructor that will initialize all the attributes. Grid, grid, parentheses, and curly brackets. Num rows equals 20, num cols equals 10. Now let's make the cell size to be 30 pixels. Cell size equals 30. The next step is to initialize the grid array with zeros. For that, let's create another method and call it initialize. So we have to go back to the header file. We can press Alt+2 and go back to it at once. It is the second open tab in VS Code, so we can use this keyboard shortcut if we wish. This method is going to be public because we are going to use it from other parts of the program. So we type here, void initialize. Now back to the implementation file, Alt+3. Let's implement this method. Void grid initialize parentheses and curly brackets. Now we need to loop through all the elements of the array and give them the value 0. For int row equals 0, row less than number of rows, row plus plus. For int column equals 0, column less than number of calls, column plus plus. Grid brackets row brackets column equals 0. Let's call this method in the constructor. We type initialize here. Now that the grid is full of zeros, let's print it at the terminal to see if it works. Let's create a method for it. Again, back to the header file. Let's create a public method named print. Void print. Now in the implementation file, we create the method implementation. Void grid print parentheses and curly brackets. Again, we have to loop through all the elements of the grid and print the value of each one at the terminal. For int row equals 0, row less than number of rows, row plus plus. For int column equals 0, column less than number of calls, column plus plus. Now we need to print each value, so let's include a library for this. At the top of the file we type include IOStream. Back to our method now. std cout grid brackets row brackets column and a space in quotes. And outside the second for loop, std cout std end line. That's it, the method is ready. This method will be useful if we want to see the state of our grid later on. Let's now create a grid object in the main file and print it to see if everything works as expected. Alt+1 to go back to the main file. Now we have to import the grid class, so include quotes grid.h. Now we can create a grid object. Grid equals grid. Now we can call the print method, grid.print. And now let's run the program. Cool, as you can see, at the terminal we can see all the contents of the grid. A 2D array filled with 0. Our grid is ready. Now let's go back to the grid class to work on it a little more. At +2 and VS Code gets me back to the grid class header file. What else do we want the grid to know about? The grid must also know the colors to use to display each cell. So let's create a data structure to hold all the colors it will use. The easiest C++ data structure we can use is a vector. A C++ vector is a container that can hold multiple values of the same data type, like a list or an array, but with some additional features, such as the ability to easily add or remove elements and to dynamically resize itself. To use a vector, we first have to include it, so we type include vector at the top of the file. We also need to include the raylib library, since the vector is going to hold color structs from the raylib library, so we type include raylib.h. Now we are ready to define the vector attribute. Let's make it private. std vector color colors. As we said, we have 7 blocks in the Tetris game and each block has its unique color. So we are going to need 7 colors for the cells of the blocks and 1 color for the empty cell, a dark gray color. Let's create a method that will return a vector containing 8 colors and let's make it private. std vector color getCellColors parentheses. Now let's go to the implementation file to create the method and the colors. std vector color grid getCellColors parentheses and curly brackets. As we said, a color is just a struct of 4 values, so let's create the structs. Here are all the colors. I have created a struct of type color for each color and a struct for the color of the empty cell, this one. Now let's put all of them in a vector and return that vector. Return curly brackets dark gray, green, red, orange, yellow, purple, cyan, blue. The order of the colors in the vector is important. We are going to use the index of each color later on when we draw each cell on the screen. The index corresponds to the block ID, but more on that in a minute. So in the constructor, we can now load the list of colors. Colors is equal to getCellColors. That's it. The constructor method of the grid class is ready. Now we are ready to draw the grid. Let's create a draw method. Back to the header file. The draw method is going to be public. Void draw. Now back to the implementation. Void grid, draw, parentheses and curly brackets. We need to draw each cell of the grid with a specific color. With dark gray color if the cell contains 0, with green color if the cell contains the value 1, and so on. So first we have to get the value stored in each cell of the grid. We will use a nested for loop for this. For int row equals 0, row less than number of rows, row plus plus. For int column equals 0, column less than number of calls, column plus plus. Int cell value is equal to grid brackets row brackets column. This code iterates through each cell in the grid and assigns the value of that cell to the variable cell value. Now it is time to draw this cell on the screen and give it a color. Now before we draw something, let's talk about how raylib draws simple shapes on the screen. Raylib provides various functions to draw simple shapes on the screen, including rectangles, circles, lines, and polygons. When using any of these functions, you need to specify where on the screen you want the shape to be drawn. For instance, to draw a square, we can use the drawRectangle function. This function takes 5 arguments: the x and y coordinate of the top left corner of the square, the width and the height of the square, and a color. In our game, the cells are square, so we will use the drawRectangle function to draw the cells of the grid. Let's go back to our code. So inside the draw method of our grid object, let's draw a square. Draw rectangle, parentheses, x, y, w, h, color. We need to know 5 things to draw a cell of the grid as a square. The x and y coordinate of its top left corner, its width, its height, and its color. The x is going to be column, but since we are using a grid, we have to multiply this by cell size. Column times cell size. We do the same thing for the y. Row times cell size. Now the width is going to be cell size and the height is also going to be cell size. The last argument we have to provide is the color. The color is a color stored at the colors vector. But which one? We can use the cell value variable to index into the colors vector and retrieve the color struct for that specific cell. So we type colors brackets cell value. Since our grid now only contains zeros, the cell value variable will be 0, so this will return the first color of the vector, which is a dark gray color. That's it, our draw method is ready. Let's use it in our code. Let's go back to the main file and call the draw method of the grid object we have created inside the main loop. So after the clear background dark blue method, we type grid.draw. Let's run the program. When we run the game, we can see a gray screen because all the cells are the same gray color and there is no visible space between them. To make the cells visible, we need to add a margin of 1 pixel to each cell. Our cell size is 30 by 30 pixels, so we can draw a 29 by 29 pixels gray rectangle for each cell to create the margin. This way, the grid lines will be visible, making the game more understandable and easier to play. Let's do it. In the draw method of the grid class, in the drawRect method, we need to make some changes. We need to add +1 here and here. This way, we add a 1 pixel offset at the x and y position of the gray rectangle we are drawing. Also, we need to subtract 1 pixel from the width and the height of the rectangle we draw because we said we need it to be 29 pixels. That's it. If we run the game once more, we can see that the grid lines are now visible. Beautiful, our grid is visible. Now let's modify the values of some cells to see if our grid can display them in different colors. So in the main.cpp file, outside of the game loop, let's hardcode the values of some cells as a test for our grid class. Let's set some values in the grid. Firstly, we will make the top left cell hold the value 1. Grid.grid bracket 0 equals 1. I can duplicate this line by pressing Shift, Alt and the down arrow key. Next, let's make the cell at the 4th row and 6th column hold the value 4, and the cell at the 18th row and 9th column hold the value 7. It is important to know that the counting for the rows and the columns starts from 0, so the 4th row is actually the row with index 3. Let's run the game again to see the changes we made. Great! Now we can see that the cells are displayed with different colors, indicating that the game is functioning as expected. Additionally, we can check the console to see the values of each cell, including the ones we have just changed in the code. Perfect! We have just completed step number 2. Congratulations on making it this far in the tutorial. You are doing great. Let's keep going and continue building our Tetris game. The next step is to create the blocks of the game. As you know, Tetris is a game where you have to fit different shapes made of 4 tiles each. There are 7 types of shapes in total, called tetrominos. When you start the game, the blocks appear in a certain way. The blocks in Tetris can spin around a point, usually in the middle of one of their tiles. For instance, the T-shaped block rotates around the center tile. The I block and the O block in Tetris rotate differently than the other blocks. The I block rotates around a point that isn't in the center of a tile, while the O block doesn't appear to rotate at all. To represent the blocks, we imagine a box around each block that's big enough to fit in all 4 rotation states. The box is divided into a grid, and we label the top left cell as the origin, row 0, column 0, just like in the game grid. For each of the 4 rotation states, we store which cells are occupied in this grid, not all the cells of the grid. Let's use an example to make this clearer. Imagine the T block in Tetris. We draw a box around it and we divide it into a grid with 3 rows and 3 columns, making it 9 cells in total. However, we only need to store the cells that the T block occupies, not the whole grid. If the T block is in its first state 0, we only need to store the values 0, 1, which means that the cell in row 0 and column 1 is occupied. We also need to store 1, 0, 1, 1, and 1, 2 for the other occupied cells. We repeat this process for the T block's remaining 3 rotation states, storing only the occupied cells for each. This is how we represent all the blocks in Tetris, using this same process for each one. Using the bounding grid approach to represent the blocks has a big advantage. It makes rotating the blocks much easier. To rotate a block, all we need to do is to update a state variable that indicates the current rotation state of the block and modify the occupied cell stored in the grid accordingly. This means that we don't have to calculate the new positions of each tile in the block, which can be complex and time-consuming. Instead, we simply update the occupied cells in the bounding grid, and the game engine takes care of displaying the block in the correct rotated state. Okay, now that we know how to represent each block using the bounding grid approach, let's return to our code and start implementing it. Now, before we start coding, let's leverage an object-oriented feature to simplify our code: inheritance. Inheritance is like passing down traits from parents to children. C++ allows us to create a new class that is a modified version of an existing class. This new class, called the child class, will inherit all the attributes and the methods of the original class, called the parent class. Then we can add new attributes and methods or override the inherited ones in the child class to customize its behavior. This way, we don't have to repeat the same code for similar classes, and we can make changes to the parent class that will affect all the child classes. It is like having a template that we can reuse and modify without starting from scratch every time. In this game, we have 7 different blocks, but they all share some common properties and behaviors. Instead of creating separate classes for each block, and duplicating the same code, we can create a base block class with the shared code and characteristics, and then create 7 new classes for each block that inherit from the base class. This means that each of the new classes will automatically have all the properties and behaviors of the base class without needing to repeat the code. Using inheritance helps us to simplify our code and make it more efficient. If you haven't used inheritance before, it's not a problem. It's actually a simple and powerful feature of object-oriented programming. Once you understand how it works in this game, you'll be able to apply it to other projects as well. Let's start by creating the block class, the base class for all the blocks. Let's create a new header file and call it block.h. Now, we type pragma once, class, block, curly brackets and a semicolon, public colon and private colon. Now the first public method is going to be the constructor, so we type block parenthesis semicolon here. To create a block class, we need to determine what information each block needs to store. The most important thing is to distinguish between different blocks, so each block will have a unique ID. To add this attribute, we can create an ID attribute in the class and we will make it public so we can access it from other classes. Int ID. To represent the cells that the block occupies in a 4x4 grid for all rotation states, we will create an attribute called cells. This attribute will be a map of vectors that will hold the position of each occupied cells on the grid. So we need to do some work before being able to create the cells attribute. As we said, we need a map of vectors. But what is a map in C++? In C++, a map is a container that stores elements in key-value pairs, where each element is associated with a unique key. It allows for efficient retrieval of values based on their corresponding keys. So we're going to use a map. The key is going to be the rotation state of the block, and the value is going to be a vector containing the positions of the occupied cells. Let's create a position class to make our lives a little bit easier. Let's create a new file and name it position.h. And now let's create the position class. This class will have a constructor that will take a row and a column as an argument. Pragma once, class, position, curly brackets and a semicolon, public colon, position, parenthesis, int row, int column. Also, this class will have a row and a column attribute, int row, int column. Now let's create the implementation file. Ctrl+N to create a new file and Ctrl+S to save it as position.cpp. Now the first thing we have to do is to include the header file. Include quotes position.h. Now let's implement the constructor. Position, position, parenthesis, int row, int column. This dash greater than row equals row and this dash greater than column equals column. The this keyword is used to refer to the current object, and the this dash greater than, which looks like an arrow, is used to access a variable within the object. So this expression assigns the value of the row parameter to the row attribute of the current object. Similarly, this expression assigns the value of the column parameter to the column attribute of the current object. Cool, the position class is ready, and now we can represent a position on the grid with a single object. We can close this file now, and the position.h file as well. We won't need to open them again. Now we can finally create the cells attribute. As we said, it will be a map of vectors, so in the block.h file, let's include these classes. Include vector and include map. Lastly, we need to include the position class we just created. Include position.h. Now let's create the attribute std::map. The map will contain a key, which will be an integer, so int here, and the values which will be a vector of position, so std::vector position cells. Next, we need to know the size of each cell of the block in pixels. So the next attribute will be a private one, int cell size. The next thing we need to know is the rotation state of the block. So let's create a new private attribute named rotation state, int rotation state. The last thing we need to know for the block for now is the colors it has to use to draw each occupied cell on the screen. The colors are the same ones we used in the grid class earlier, so we can copy the method from the grid class and paste it in the block class. However, this will result in duplicate code, which is not a good programming practice. We want to avoid duplicate code as much as possible to keep our code organized and easy to maintain. So we will create another file to hold all the definition of the colors and use it in both the grid and block classes. We press Ctrl+N to create a new file and Ctrl+S to save it as colors.h. Now we type pragma once. We also need to include raylib since we will be using the color struct from it. Include raylib.h. Now let's declare all the colors. Let's do the first one. Extern const color dark gray. Using the extern keyword allows us to declare a variable in one file and use it in another, making it easier to share data across different parts of our program. The const keyword specifies that the value of the variable cannot be changed during program execution. Similarly, we declare all the colors we use in our game so far, like this. Now, let's define all the colors in a .cpp file. Let's create a new file and name it colors.cpp. We have to include the header file, so include colors.h. Now let's copy the color definitions from the grid.cpp file. I just copy these values and I paste them here. Now all I need to do is to add the const keyword at the beginning of each color definition. Perfect. Now let's create a simple function that will return a vector with all the colors in a specific order, just like we did in the grid class. std : vector color get cell colors. And we simply return a vector of all the cell colors. We use the same return from the getCellColors method of the grid class. We can simply copy it from the grid class and paste it here. Cool. The last step we have to do is to define this function to the header file. We go back to the colors.h file and we type std : vector color getCellColors parentheses and a semicolon. And since we are using the vector class, we have to include it. Include vector. We are now ready to use our colors.h header file in our code. First of all, let's use the colors header file in the grid class in the grid.cpp file. Let's include it. Include colors.h. Now we don't need the getCellColors method anymore, so we can remove it. We also have to remove the method declaration from the header file. So we open the grid.h file and we remove the method declaration like this. Now, back in the .cpp file, in the constructor, we don't have to change anything. The getCellColors function now lives in the colors.cpp file. Our grid class is ready. Let's run our program again to see if everything works. Cool, our game works with the new colors header file just like before. Now let's go back to the block class. First, we are going to include the colors header file. Include colors.h. As we said before, we need a colors attribute. Let's create it. std : vector color colors. Now we are ready to implement the constructor of this class. Let's create a new file and call it block.cpp. First of all, we type include block.h to include the header file. Now we type block : block parentheses and curly brackets. Let's initialize some of the attributes. We won't initialize the ID in this class. We will do this in the child class. We will initialize the cell size. Cell size is equal to 30. We will also initialize the rotation state. Rotation state is equal to 0. Lastly, we will initialize the colors vector. Colors is equal to getCellColors. Perfect. That's it. We now have a vector containing all the colors we need to use to draw a block on the screen. The block class will also have a draw method that will be responsible for drawing the block on the screen. Let's create this method. Void block : draw parentheses and curly brackets. VS Code underlines this method because we haven't declared it yet in the header file. We select the Quick Fix button here and we let VS Code create the declaration for us to save some typing. Cool, it automatically declared the method. Now let's go back to the block.cpp file. Now we need the position of each occupied cells of the block in order to draw it on the screen. But we don't have this information yet, so we have to create it. To simplify our code, we will use inheritance. We will create a separate class for each block which will contain the cell positions for each rotation state. These classes will inherit from the block class. Let's create a new file and let's name it blocks.cpp. Inside this file, we will create all the child classes, one for each block. First of all, let's import the two required classes, include block.h and include position.h. Now let's create a class for the L tetromino. Class lblock, curly brackets and a semicolon. As we said, this block must inherit the attributes and the methods of the block class. So we have to declare that here, colon, public, block. Now the lblock class is a child of the block class. Now let's create a constructor for this lblock class, public, colon, lblock, parentheses, and curly brackets. Let's give this block a unique ID, ID equals 1. Now all we have to do is to define which cells are occupied. We are going to use the cells attribute of the block class. As we said, the cells attribute is a map of vectors. The key of this map will be the rotation state, a value from 0 to 3. So the map is going to have 4 keys. Let's do it. The first key is going to be 0, so we type cells bracket 0 equals 2. Now we need a vector with all the occupied positions of the L block in the rotation state 0. Which cells are occupied when the L block is at the rotation state 0? Cells 0, 2, 1, 0, 1, 1, and 1, 2. Let's create a vector with these cells using the position class. Curly brackets, position 0, 2, position 1, 0, position 1, 1, and position 1, 2. That's it. The rotation state 0 is ready. Now we need to do the same thing for the other 3 rotation states. I will leave this as an exercise for you to practice. Based on the given graphic, please fill in the missing data. Take your time to work on it, and when you are ready, you can resume the video to see the solution. Welcome back! I hope you were able to successfully complete the exercise and that it helped you better understand what we are doing. So that's the complete class. I have filled in all the data for all the rotation states. We have to do the same thing for all the blocks. But before that, let's draw the first shape on the screen. Let's go back to the block class and work on the draw method. Now we have access to all the cells of the block for every rotation state. Check this out. std : vector, position, tiles, equals to, cells, brackets, rotation state. This line retrieves the vector of positions for the current rotation state of the tetromino as determined by the value of the rotation state attribute. Since the rotation state is now 0, we get the vector that corresponds to the key 0 of the cell's map. Now, for each cell, we can draw a rectangle. We're going to use a for loop. For position, item, colon, tiles, curly brackets. Now we need to create a rectangle for each cell. For this, we're going to use raylib and the draw rectangle function. Draw rectangle, parentheses, x, y, w, h, color. Again, we need the x and y position of the tile we are going to draw. Item.column times cell size plus 1, item.row times cell size plus 1, the width and the height will be cell size minus 1. As we did in the grid class, we leave a 1 pixel offset when we draw the cells. That's it. The color value of the cell is obtained from the colors vector using the block's ID as the index. Cool. Let's now use this method and see a block on the screen for the first time. Back to the main.cpp file. Include the blocks file. Include blocks.cpp. Now let's remove the following lines of code from our main file, since we use them for testing purposes only and they are not needed anymore in our final implementation. Now let's create an L block. L block is equal to L block, parenthesis and a semicolon. Now in the game loop, let's draw this block by calling the draw method. Block.draw. Let's run the game. The L block has appeared on the screen. How exciting! After all the code we have written, it's rewarding to finally see a block rendered on the screen. If you have made it this far, congratulations! You have accomplished the most challenging part, and things will start to progress more quickly from now on. Now we need to create classes for the remaining 6 blocks of the game. To do this, we will go back to the blocks.cpp file and we will create a separate class for each block, such as the I block, the J block, the S block, etc. For each class, we will define a unique ID and the positions of the occupied cells for each rotation state, similar to what we did for the L block. Once we have all the block classes defined, we can easily create instances of each block type in our main program. As an exercise, take a moment to write the remaining classes yourself. I will provide you with all the data you need for each block. Simply use the same format as we did with the L block class and fill in the positions of the occupied cells for each rotation state. Here comes the data. Pause the video for each block and fill in the data. Okay, as you can now see, I have completed writing the code for all subclasses. I hope it was easy for you as well. The only tricky block is the O block, which has the same occupied cells for every rotation state, and we can simply use the same vector for every rotation state, or we can use just one rotation state now and deal with it in code later. I'll choose this option. Let's only leave one rotation state in each map. We are ready to test all the blocks. Let's go back to the main file and let's draw a T block. Let's change this line of code. T block is equal to T block. Now if we run the game, we can see the T block displayed. Cool, we can display all the blocks like this. Great job, we have completed step number 3. We have made a lot of progress. Now let's work on the next step. Let's write code to move the blocks on the screen. First of all, let's think about the problem. So far, we have created a game grid, and on top of that, we are displaying only the occupied positions of a smaller grid, the block grid. The origin for both grids is the top left corner. So if we want to move the block, all we have to do is to move its origin point. For example, let's say the current position of the block is at the top left corner of the grid, which is at position 0,0. If we want to move the block 3 columns to the right and 5 rows down, we just need 2 variables to hold the offset in the x and y axis on the grid. Let's call these variables row offset and column offset. To move the block 3 columns to the right and 5 rows down, we will set column offset to 3 and row offset to 5. Then we will simply add this value to the row and column positions of the block's origin point. So the new position of the block's origin point will be 5,3. This will move the block 3 columns to the right and 5 rows down on the grid. Let's implement this in code. Let's go back to the block code. So let's open the block.h header file. As mentioned earlier, we need to offset the positions of all cells in a block to move it. One way to do this is by adding 2 attributes to the block class. These attributes will hold the row and column offset of the block on the game grid. We can then update the position of each cell by adding the offset to its current position. Let's do it. Let's create 2 private attributes. Let's call the first one row offset, int row offset. Let's also create the second attribute and call it column offset, int column offset. Now let's go to the constructor in the block.cpp file and initialize these values. Row offset is equal to 0 and column offset is equal to 0. Now let's create a method that will move the block by adding a row and a column offset to the cell. Void block move parentheses int rows int columns and curly brackets. We need to know how many rows and columns we have to move. Of course, we also need a declaration of this method in the header file. Let's do it automatically. Control plus period, and we select to create the definition automatically. Perfect. Let's go back to the implementation and work on the method. Now all we have to do is to change the offset attributes. Row offset plus equals rows and column offset plus equals columns. Now we need to modify the positions of the cells in the block according to the offset. To achieve this, we can create a new method in the block class which will calculate the actual position of each cell after the offset is applied. It's better to have a separate method for this rather than modifying the positions in the draw method, because we will need to recalculate these positions later to check for collisions. This way we can avoid repetitive calculations. So let's create a new method called getCellPositions. This method will return the positions of the occupied cells with the offset applied in a vector. So we type std : vector position block : getCellPositions parentheses and curly brackets. Again, Ctrl plus period and enter on the first option to automatically create the declaration in the header file. Now back to the implementation. First, let's get the default cell positions for the current rotation state. std : vector position tiles is equal to cells brackets rotation state. Now let's create a new empty vector to hold the move tiles. Vector position move tiles. Now we need to loop through all the tiles and add the offset to their positions. For position item : tiles curly brackets position new pos is equal to position parentheses item.row plus row offset, item.column plus column offset. Now we just have to push back the new position to the move tiles vector. Move tiles dot pushback parentheses new pos. And when the loop ends, we have to return the vector. Return move tiles. That's it, our method is ready. Let's use this method in the draw method to draw the block with the updated positions. We change this line here. Tiles is equal to getCellPositions. That's it. Let's test the game. Let's go to the main file. We have created a block. Let's move the block to the right 3 cells and to the bottom 4 cells. Block.move parentheses 4, 3. If we now run the game, we can see the block in its new position. Beautiful. We can now move the blocks of the game, but the blocks spawn at the top left corner of the grid. If we look at the online version of the Tetris game, the blocks spawn at the middle of the grid. Let's implement that. One easy way to do this is to alter the child class for each block. So we will move each block 3 cells to the right. So in the blocks.cpp file, we alter all the constructors like this. Move parentheses 0,3. I do the same for all the blocks one after another. Now let's go back to the main file, remove the move method call from here, and let's run the game again. As you can see, the block moved to its proper position. There are only 2 exceptions. The first one is the O block. If we create an O block, we can see it is not centered. We have to move it 1 cell to the right. So we go back to the O block class definition and we change the move call to 0,4. If we run the game once more, the O block is now centered correctly. The other exception is the I block. As you can see, if I create an I block, it is centered, but there is an empty row above it. We have to move it 1 cell to the top. So we go back to the I block class definition and we change the move call to -1,3. If we run the game one more time, our I block is centered correctly. Beautiful. Moving on, we can now add input controllers to move the block left and right. But before we dive into input controls, let's take a moment to organize our code for better management and maintainability. To improve code organization and make it easier to manage in the future, we will create a game class to hold the grid and the block objects as well as various methods. The game class will serve as a container for all the elements of our game, such as the grid, the current and next block, and the game state. It will also hold methods that manage the game's logic, such as updating the block's position, checking for collisions, etc. By centralizing all the game's functionality within this class, it will be easier to understand, maintain, and expand upon in the future. Additionally, it will also improve code readability and reduce the risk of bugs by keeping related code together in one place. Overall, creating a game class will greatly improve the organization and structure of our code base, making it easier to work with in the future. So let's create a new game class. We create a new file and we call it game.h. Now we type pragma once, class game, curly brackets, and a semicolon, public colon, and private colon. Now let's define the constructor. Game parentheses. The game class must create and hold a grid. So let's include the grid class we have created. Include grid.h. Now we create a grid attribute. Grid. The next step is to create an attribute to hold the current block that is visible on the screen. But to do this, we have to select a random block from all the available blocks in the game. So let's first create a vector that will hold all the blocks. This attribute can be private. std::: vector block blocks. We need to include all the block classes, so we also have to type include blocks.cpp. Now let's create the implementation file. We create a new file and we name it game.cpp. First, we need to include the game class header file. Include game.h. Let's implement the constructor. Game, : game, parentheses, and curly brackets. First, let's create the grid object. Grid is equal to grid. Now let's create a vector with all the blocks we can use in our game. Blocks is equal to curly brackets, I block, parentheses, J block, L block, O block, S block, T block, Z block. Now we can create a method that returns a random block from this vector, so we are going to include random. Include random. Now let's create the method. Block game, : get random block, curly brackets. We also need a declaration for this method in the header file. Again, let's do it automatically like this. Perfect. Instead of randomly selecting a block from the vector every time we call the method, in the original game, each of the 7 blocks appears at least once before reappearing. So we need to implement a way to cycle through the list of blocks, ensuring that each block appears at least once before repeating the cycle. So let's first select a random block from the vector. Int random index is equal to rand, parentheses, %, that's the modulo, blocks.size. With this line of code, we get a random value from 0 to 6. We will use this number to index the blocks vector. Block is equal to blocks, brackets, random index. Now we need to remove it from the vector, so the next time the method is called, this block will not be available. Blocks.erase, parentheses, blocks.begin plus random index. Now we can return that block. Return block. Lastly, at some point, the vector will be empty, meaning no more blocks will be available. In that case, we can simply refill the vector with all the blocks again. So before selecting a random block, we have to check if the vector is empty. So we type if blocks.empty, parentheses, and curly brackets, then we recreate the original vector of blocks. We can copy the vector of blocks from the constructor, but I think it is a good idea to create a function that will return a vector with all the blocks. So let's create a new method for this. std::: vector block game : get all blocks, parentheses, and curly brackets. Again, we have to declare that function to the header file. Okay, we are ready. The declaration is now in the game.h file. So in the game.cpp file, we can define or implement this function. This function will only contain a single line of code, return, and then we have to return the vector with all the blocks. We can copy this line from the constructor and paste it here. Now we can go back to the getRandomBlock method and add a call to the getAllBlocks method we just created. Inside the if statement we add blocks is equal to getAllBlocks. Perfect, the method is now complete. We can also call the getAllBlocks method in the constructor, where we create the original list of blocks. Again, blocks is equal to getAllBlocks. We can now create the two attributes for the current and the next block. Let's go to the header file to declare the two new private attributes to the class: block current block and block next block. Now back to the implementation file. Let's initialize these two attributes in the constructor. Current block is equal to getRandomBlock and next block is equal to getRandomBlock. Of course, the game class will also have a draw method which will be responsible for drawing all the objects on the screen. Let's create it. Void game : draw parentheses and curly brackets. Let's also declare this method in the header file. Control plus period and then enter. VS Code automatically creates the declaration for us. Now back to the game.cpp file, we can just call the draw methods of the grid and the current block objects. Grid.draw and currentBlock.draw. With this, the first version of the game class is ready. Now let's test it out. In the main.cpp file, we remove all the objects we created before and the calls to the draw methods of these objects in the game loop. Also, we remove these includes as we no longer need them. But we have to add another include statement. We need the game class now. So we type include game.h. We can now create a game object. Game is equal to game. And in the game loop, we type game.draw. That's it. If we now run the game once more, we can see it is working like before, but our code is more readable and easier to work with, as you're going to find out later. Let's move on to the next step of the game development, which is to make the player move the block. So let's add keyboard controls to the game. In order to control the movement of the block, we need to detect when the player presses certain keys on the keyboard. To do this, we add a new method to the game class. Let's open the game.h file and create a declaration for a public method named handleInput. Void handleInput, parentheses. And now we can press Ctrl plus period and then enter to create the implementation automatically. We can detect if the player has pressed any key on the keyboard using the getKeyPressed method raylib provides. This function returns the key code of a pressed button, so let's use it. Int keyPressed is equal to getKeyPressed, parentheses. We got the key code of the key that the user pressed and we saved it in a variable. Now we have to check which key has the user pressed and act accordingly. We can use a switch statement. Switch, parentheses, key pressed, curly brackets, case, key left, break. This line of code checks if the key pressed variable is equal to the key left constant, which means that the player has pressed the left arrow key. Look how easy it is to detect user input with raylib. If the player presses the left arrow key, we have to move the block one cell to the left. We can achieve this by using the move method of the block class to move the block one column to the left. However, instead of calling the move method of the block directly, we will create a new method called moveLeft in the game class, as we want to encapsulate the game logic for handling the movement of the block. You are going to find out why in a minute. So let's create a new method named moveBlockLeft. Void game : moveBlockLeft. Again, we need to declare this method in the header file like this. Now, back in the game.cpp file, all we have to do is to call the move method of the current block, currentBlock.move, parenthesis, 0, -1. This way we move the block to the left. Now let's create two more methods for moving the block to the right and down. Void game : move block right, parenthesis, and curly brackets. currentBlock.move, parenthesis, 0, 1. Of course, we also need to declare this method in the header file. We do it just like before. Now, in the game.cpp file, let's create yet another method. Void game : move block down, parenthesis, and curly brackets. We also have to declare this method in the header file. currentBlock.move, parenthesis, 1, 0. Cool! In our implementation file, let's now call the methods we just created in the handle input method. Case key left : move block left. Case key right : move block right, break. Case key down : move block down, break. The last step is to call this method inside the game loop. So we go back to the main.cpp file and we call this method like this: game.handleInput. Let's now run the game. It is beautiful to see our game in action, with the ability to move the block to the left, right, and down. However, we have encountered a problem. The block is able to move outside of the game window from the left, right, and bottom edges. We need to address this issue by implementing boundary checking to prevent the block from moving beyond the game window. The solution to this issue is straightforward. Since we know that the game grid contains 20 rows and 10 columns, we can simply check the current position of each tile of the block. If any of the tiles has moved outside of the game window, we need to move it back within the boundary of the game window. Let's implement this. First of all, let's open the grid.h file and add a new method in it. We are going to create a method that will check if a given cell position is outside of the grid. Bool is cell outside, parenthesis, int row, int column. Control plus period, and then enter. Now let's implement it in the grid.cpp file. If, parenthesis, row greater than or equal to 0 and row less than number of rows, and column greater than or equal to 0 and column less than number of calls, curly brackets, return false. If the position, row and column is inside the grid, we return false, else we return true. Return true. Now let's go to the game class in the game.h file and add a new private method that will check if a block is outside of the game window using the isCellOutside method of the grid class we just created. Bool isBlockOutside. Now let's create the implementation automatically once more. Control plus period, and then we select create definition. Cool. First we need to get the list of all the tiles or cells of the block. std : vector position tiles is equal to current block dot get cell positions. Now we need to check if any tile of the block is outside of the grid. For parenthesis position item tiles curly brackets if parenthesis grid dot is cell outside parenthesis item dot row item dot column. If the tile is outside of the grid, return true, else return false. Our method is ready. Now we can modify the move block left, move block right, and move block down methods to check if after moving the block it is still inside the game window. So inside the move block left method we add the following code. If parenthesis is block outside, if the block moves outside of the game window, we have to move it back in, so we undo the move. Current block dot move parenthesis 0, 1. We do the same thing for the other two methods as well. If parenthesis is block outside, current block.move parentheses 0, -1. And if isBlock outside, current block.move parentheses -1, 0. Now we can run the game once more. Perfect! The game works and the block cannot move outside of the game window. Keep up the good work. We are making steady progress towards completing our game. Let's remove step number 4 from the list. Moving on to the next step, which will take us just a few minutes. We now need to rotate the block. Luckily, since we have already entered all the data for each rotation state for each block, we don't have a lot of work to do to rotate a block. Let's go to the block class in the block.h file and create a public rotate method for the block, void rotate. We now create the implementation of the method, Ctrl+period, and then enter. Inside the method, we simply have to increase the rotation state by 1, rotation state ++. We also need to check if the rotation state is equal to the number of rotation states the block has. Typically, blocks have 4 rotation states, except for the O block, which only has 1. If the rotation state reaches the maximum number of states for the block, we need to reset it back to 0. We can implement this by adding a conditional check after incrementing the rotation state. If rotation state equals cells.size. This approach applies to all the blocks in the game, including the O block. We have to cast this number to an int to make the compiler happy, else it will give us a warning. Now we type rotation state equals 0. Now we have to go to the game class in the game.h file and create a rotate method. This method will be private, only the game class will call it. Void rotate block. Let's implement it in the game.cpp file. Current block.rotate. Now, in the handle input method, we will assign the action of pressing the up arrow key to rotating the block clockwise. So we add the following. Case key up, rotate block. Break. Let's run the game. Perfect. The game works. We can move the block and we can rotate the block each time we press the up arrow key. However, there is an issue with our code. When we rotate the block, it may end up in an invalid position where some of its cells are outside of the game window. This is something we need to prevent. Luckily, that's easy to fix. After rotating the block, we will check if the block is inside the game window. If it is not, we will undo the rotation. So first, let's create the undo rotation method in the block class. So in the block.h file, let's create a public undo rotation method, void undo rotation. This method is similar to the rotate method. Now, let's implement it. Rotation state -. We just set the rotation state of the block to the previous one. The only thing we have to check is if the rotation state is -1. In that case, again, we will reset it to the max value it can get. If rotation state equals -1, curly brackets, rotation state is equal to cells.size -1. Now we have to go to the game class in the game.cpp file and modify the rotate block method to check if the block moves outside of the game window after rotating. If isBlock outside, curly brackets, then we have to undo the rotation. That's easy. Current block.undo rotation. We are now ready to test the rotation in our game. Let's go to the main file and run the program once more. Beautiful. The game works and the rotation works, and the block cannot rotate to an invalid position. The game won't let us. Perfect. One more step is now complete. Now let's work on the collisions. First, we have to implement the automatic dropping of the block in a way similar to the Tetris game. To achieve this, we can call the moveBlockDown method of the game class in the game loop. This will ensure that the block gradually moves downward on its own without any user input. So after the game.handleInput call, let's add this line of code to see what happens. Game.moveBlockDown. Now, if we run the game, we can see that the block drops, but way fast. Why is this happening? The game loop is executed 60 times per second, so the game.moveBlockDown method is called 60 times per second. This causes the block to move 60 cells to the bottom every second, which is why it moves so quickly. Instead of calling the game.moveBlockDown method in every execution of the game loop, we need to update it at a slower rate, for example, every 200 milliseconds. This will slow down the block's movement and make it more visible on the screen. To achieve this, we need to create a function called eventTriggered that will be used to check if a certain amount of time has passed since the last update of the game. We can use this function to control the update rate of the game. By setting a time interval of 200 milliseconds, for example, we can ensure that the moveBlockDown method is only called every 200 milliseconds, which will slow down the block's movement. First of all, let's create a variable named lastUpdateTime here at the top of the file and initialize it with 0. Double lastUpdateTime is equal to 0. The lastUpdateTime variable is used to keep track of the time at which the last update of the game occurred. This variable is initialized to 0 when the game starts. Now let's create a new function up here called eventTriggered. We want to see if some interval has passed, so we will return a boolean value. So bool eventTriggered parentheses and curly brackets. Now this function is going to take an interval in seconds as an argument. So we type here double interval. Now we are going to use the getTime function from raylib to get the current time in seconds since the program started running. Double current time is equal to getTime. We assign this value to a variable called current time. We then compare the difference between the current time and the last update time variables to the specified interval argument. If current time minus last update time greater or equal to interval, curly brackets. If the difference is greater than or equal to the interval, it means that the interval has passed since the last update. So we update the last update time variable to the current time and return true. Last update time is equal to current time, return true. Otherwise, we simply return false. Great, our function is ready. We are going to call this function 60 times per second because we are going to call it inside the game loop. Let's do it. We want to update the position of the block every 0,2 seconds. So, if eventTriggered parentheses 0,2 curly brackets, if the function eventTriggered returns true, it means the interval has passed, so we have to move the block down. So game.moveBlockDown. It is important to remove the call to the game.moveBlockDown method that was previously in the game loop to avoid updating the block's position more than once per interval. With this setup, let's run the game once more to see if the changes have taken effect. As you can see, the block is moving at a slower pace, which is exactly what we want. However, we now face another issue. When the block reaches the bottom of the screen, it does not lock in place, and we can still move it right and left. This is not the desired behavior, so let's address this problem. To fix this issue, we need to implement the locking mechanism for the block when it reaches the bottom of the game window. This will ensure that the block locks in place and becomes immovable once it reaches the bottom. In other words, we have to change the grid values to hold the position of the block when it reaches the bottom of the window. So, in the game class, in the moveBlockDown method, we check if when moving down the block, it gets out of the game window. In that case, we undo the move. This is when we must lock the block in place. Let's call the lockBlock method, which we will create at once. In the game.h file, let's create a private method named lockBlock, void lockBlock. Now we press Ctrl+period and then Enter to allow VS Code to create the implementation of this method in the CPP file. In this method, we need to update the game grid values to represent the location of each cell of the block on the grid at the time it touches the bottom of the screen. For each cell, we will store the ID of the block in the corresponding cell of the game grid. The ID value corresponds to the block's color. This will mark the cells as locked and indicate that the block has reached its final position at the bottom of the game window. First, let's get the current positions of all the tiles of the block. std::vector position tiles is equal to current block dot get cell positions, parenthesis and a semicolon. Now, for each cell position, we will store the ID of the block in the grid. For parenthesis, position item, colon, tiles, curly brackets, grid dot grid, brackets, item dot row, brackets, item dot column, equals current block dot ID. Now we need to spawn a new block on the screen. We already know which is the next block. It is saved in the next block attribute. So we type current block is equal to next block. And we have to update the next block attribute with another random block. Next block is equal to get random block. Let's test the game once more. Now, each time a block reaches the bottom of the screen, it locks in place and a new block is spawned. The newly spawned block cannot collide with the blocks that are already locked in place. We need to fix this problem. The solution to this is again very easy. When we move the block one row to the bottom, we need to check if the cells of the grid the block occupies are empty or not. If they are not empty, we have to undo the move and lock the block in place on the grid. So let's create a method that will check if a cell of the grid is empty or not. While we can implement this method in either the game or the grid class, it makes more sense to write it in the grid class, as it logically belongs there. So in the grid class, in the grid.h file, we create a new public method. Bool is cell empty, parenthesis, int row, int column. Let's implement it. Ctrl+period and enter. Now in the implementation of this method, we check if the cell in question holds the value of 0. If, parenthesis, grid, brackets row, brackets column equals 0, curly brackets, return true. Else return false. Great. Now in the game class, in the game.h file, let's create a private method that will check every cell of a block to see if it is on top of an empty cell of the grid or not. Bool block fits, parenthesis and semicolon. Let's implement it. Again, we get all the cells of the block. std::vector position tiles is equal to current block dot get cell positions. For parenthesis position item tiles curly brackets. Now we have to check if any of the cells is occupied. If parenthesis grid dot is cell empty, parenthesis item dot row, item dot column equals false, curly brackets. In that case, we have to return false. Else, if all the cells are empty, we just return true. The block can move to the specified position. The last step is to modify the move block down method. We need to check if the block after moving one row down is inside the game window or if the block fits in its new position. So we add or block fits equals false here. Now, if we attempt to move the block down and encounter a cell that is already occupied, we undo the move and lock the block in place. Let's try it. The game runs, and as you can see, when a block collides with another block, it locks in place. It no longer overrides it. That's very cool. Again, we have a small problem to fix though. We check if a block collides with another block only when we move the block down. Now, when we move it left or right, or if we rotate a block, this results in a similar problem as you can see. We have to fix it. Since we now have the function needed to check if a block fits in its new position, the fix to that problem is very easy. In the game class, in the moveBlockLeft method, we have to add the following check, or blockFits == false. We need to check if the block after moving one column to the left is inside the game window or if the block fits in its new position. If this is false, we undo the move. It is not a valid move. We do the same thing to the moveBlockRight method. Or blockFits == false here, and we do the same with the rotateBlock method. Or blockFits == false here. That's it. Let's test the game one more time. Good job! The game works as expected, and the blocks can only move to valid positions. We can no longer overwrite the blocks that already exist on the grid. Another step is now complete. The game logic is almost ready. The next step is to check for completed rows. All we have to do is to check if a row is full, and when it is, we have to clear it and move all the occupied cells above that row one row down. This is how we are going to do it. We will scan every row of the grid from the bottom to the top. We are going to need a variable to hold the number of completed rows. If we find a completed row, we will increase the completed variable by 1. Then we will clear the row and check the next row. If it is not completed, we will move the row down by the value the completed variable contains. This procedure works for any number of completed rows. See what happens if we find 2 completed rows. We check the first row, it is completed, so we increase the completed variable by 1 and we clear the row. Then we check the next row. It is completed, so we increase the completed variable by 1, it is now 2, and we clear the row. Next we check the next row, it is not completed, so we have to move this row down by exactly 2 rows. And with the same procedure, we check every row of the grid. Now that we know what we have to do, let's implement this in code. We need to write some methods in the grid class. First, we need to write a method to check if a row is full. So in the grid.h file, we create a new private method. Bool isRowFull parentheses int row. We are going to give this method a row as an argument. Let's implement it. Now all we have to do is to check if any of the cells in a row are empty, meaning they have a value of 0. If any cell is empty, then the row is not considered full. We need to get every column of the grid. For parentheses int column = 0, column less than number of calls, column ++ curly brackets. Now we need to check if the value of the cell is 0. If parentheses grid brackets row brackets column == 0 curly brackets. If it is, we have to return false. Return false. Else we return true. Return true. Now we need to create a method that will clear a row. In other words, it will set the value of each cell of that row to 0. Again, this method is very easy. First, let's declare it in the grid.h header file as a private method. Void clear row parentheses int row. Again, we need a row as an argument. Now let's implement it. Again, we get all the columns. For parentheses int column = 0, column less than number of calls, column ++ curly brackets. And we have to set the value of each cell of that row to 0. Grid brackets row brackets column = 0. Our method is ready. Now we need yet another method to move a row down by a specific number of rows. Let's go back to the grid.h file and create a new private method. Void move row down parentheses int row int num rows. Here we need 2 arguments, the row to move down and how many rows to move down. Again, let's implement this method. I bet you are now familiar with the keyboard shortcut. Again, we need to get all the columns. For parentheses int column = 0, column less than number of calls, column plus plus, curly brackets. Now we need to change the values of the destination row to be equal to the current row. Grid, brackets, row plus number of rows, brackets column is equal to grid, brackets row, brackets column. Lastly, we have to clear the current row. Grid, brackets row, brackets column is equal to 0. In summary, this code moves a row in the grid down by number of rows by copying the values from the original row to a new row and clearing the original row. We are now ready to create the method that will combine all these methods. Back to the grid.h file. This time, the method we are going to create is going to be a public method because we are going to use it in the game class. Int clear full rows, parentheses. In the implementation now, this method will check all the rows from the bottom to the top to see if any row is completed. So we need a completed variable. Int completed equals 0. Now we need to check every row, starting from row 19 and moving down to row 0. For parentheses, int row equals to num rows minus 1, row greater than or equal to 0, row minus minus, curly brackets. This for loop iterates through the rows of the grid in reverse order, starting from the last row and going up to the first row, row 0, with a step of minus 1 to move upward. Now we have to check if the current row is full using the isRowFull method we wrote earlier. If, parentheses, isRowFull, parentheses, row, curly brackets. If the row is full, we have to call the clearRow method to clear all the cells in the current row. Clear row, parentheses, row. And then we have to increment the completed counter by 1 to keep track of the number of rows completed. Completed plus plus. Now, if the current row is not full, but some rows have already been cleared, it means we have to move that row down. Else if, parentheses, completed greater than 0, curly brackets, move row down, parentheses, row, comma, completed. Lastly, let's return the completed rows. We will need them to calculate the score later on. Return completed. Great! Now we are ready to use that newly created function in our game. We have to go to the game class and in the lockBlock method we have to call the clearFullRows method. Grid.clearFullRows, parentheses, semicolon, here. Let's run the game once more. Now, each time we complete a row, it should disappear from the grid. Okay, let me place some blocks on the grid. Here we go. A completed row. It goes away. Perfect. Another very important step of the game is now complete. Let's work on the next step, which is to make the game end. The game ends when a newly spawned block overlaps with a block that is already locked in place on the grid, preventing further movement or placement of the new block. In our game, the new block is spawned at the top of the screen, similar to the online version of Tetris. However, in some other version of Tetris, the new block is spawned outside of the visible screen and then gradually slides into the play area one row at a time. So to check if the game has to end, all we have to do is to check if the newly created block fits in the grid. If it does not fit, the game is over. Let's code this behavior in our game class. That's easy. When we lock a block in the grid, we create a new block. Now we have to check if that new block fits in the grid. If, parentheses, block fits equals false, curly brackets. If the block does not fit, we have to end the game. Let's create a GameOver attribute to the game class and set it to false. Let's go to the header file and declare a public Boolean attribute, bool GameOver. Now in the .cpp file, let's initialize it in the constructor. GameOver is equal to false. Now we need to set this attribute to true when the game ends. So in the lockBlock method, if the block does not fit, we set the GameOver attribute to true. Game over is equal to true. Now, when the game is over, we need to stop the user from moving the block on the grid. So let's modify the methods that move and rotate the block. First, let's work on the move block left method. When the user presses any key on the keyboard, we have to check if the game is over. We have to enter all the code inside an if statement like this. If not game over, curly brackets. If the game is not over, we can move the block. We do the same thing with the other three methods. In the move block right, in the move block down, and lastly in the rotate block method. Perfect! Let's run the game with a new functionality. Let's go to the main file and let's increase the game speed temporarily. Let's check for the game over condition. As you can see, when the new block spawns on top of an occupied cell, the game immediately ends and the player is no longer able to move the block. But so far, there is no way to restart the game after it is over. That's what we're going to work on now. Let's go back to the game class and restart the game. We want to restart the game whenever the user presses any key on the keyboard. We have to modify the handle input method. Here we have a variable that holds the value of the key pressed. If no key is pressed, the variable holds the value 0. We can use it. If, parenthesis, game over, and key pressed is not 0, curly brackets. The game is over and a key is pressed. We need to restart the game, so we have to set the game over attribute to false. Game over is equal to false. And we have to reset the game. Let's call a reset method, reset. We haven't created a reset method in the game class yet. Let's create it now. In the game class header file, we create a private reset method, void reset. Now, let's implement it in the .cpp file. What do we need to do? We have to clear the grid. Luckily, we have a method to do just that in the grid class. It is the initialize method which sets all the cells of the grid to 0. It is exactly what we need. Grid.initialize. The grid is now reset. What do we have to do when the game ends? We need to select a new random current block from the vector of blocks and a new next block. But first, we have to create a new vector with all the blocks. Blocks is equal to get all blocks. And then we select a random block to be the current block and another one to be the next block. Current block is equal to get random block and next block is equal to get random block. Let's run the game one more time. Let me drop some blocks quickly to see what happens. Perfect. As you can see, the game is now over and it waits for a key press. If I press any key on the keyboard, the game starts over with a clear grid. Very cool. Congratulations! You have successfully implemented the game logic. Well done on reaching this point. Another step is now complete. Now let's work on the next step. Let's add a user interface to the game to look like this. The user interface consists of several components. A background that serves as the canvas on which all the game elements are drawn. A title text element for displaying the score. A rounded rectangle to display the score value. A text element for rendering the actual score value. A title text element for displaying the upcoming shape, the next shape. A rounded rectangle to display the next shape. The actual next block shape itself. And a title text element for displaying the game over message. These elements work together to create the visual interface for the game, providing information on the score, the next shape, and the game over condition. Let's start by creating the background. Let's go back to the main.cpp file. First, let's make the game update slower once again by changing this value to 0,2. Now, the following line of code creates the game window, which serves as the canvas on which we draw all the game elements. The game window is sized to match the dimensions of the grid. Let's give the grid an offset of 10 pixels to the left, top and bottom, and 190 pixels to the right. The new dimensions of the game window will be 500 by 620. If we run the game now, we can see that the grid is drawn from the top left corner of the game window without any offset. Let's give it a 10 pixel offset to align it properly. To properly align the grid within the game window, we need to make a change in the draw method of the grid class. We can adjust the x and y coordinates of the rectangle being drawn by adding 10 pixels to both. So we can update the expression +1 to +11 in order to achieve the desired offset. Similarly, we need to update the draw method of the block class to add 10 pixels to the x and y coordinates of the cell being drawn. This can be achieved by modifying this line to look like this, +11 here and here. Cool, let's run the game one more time. Perfect, as you can see, the background of the game is now visible. Now, moving on to the next UI element, we need to print the text score on the screen. With raylib, to create and display some text, we need to follow two steps. First, we need to load a font, and then we can display the text we want using the drawTextEx function. First, let's draw the score title. I have placed a font named monogram.ttf in the font folder in my game directory. Now, in the main.cpp file, let's load this font. We are going to use the loadFontEx function. Font is equal to loadFontEx. First, we are going to enter the path to the font, quotes font/monogram.ttf. Then we will set the font base size to 64 pixels, and then we enter 0 for the last two arguments of the function. Our font is now loaded into the GPU memory. We can now use it. Let's go to the game loop and draw the score using the drawTextEx function. This function takes several arguments. The font argument specifies the font to use, which can be loaded with the loadFontEx function. The text argument is a string of text to draw. The position argument is a 2D vector that specifies the position to draw the text at. The font size argument specifies the size of the text to draw. The spacing argument specifies the spacing between the letters. And the tint argument specifies the color to use for the text. So let's enter all this stuff into the function. drawTextEx parentheses. The font is font and the text is score. Now we need a 2D vector that specifies the position to draw the text at. Curly brackets 365,15. Now we need the font size. Let's enter 38. It works okay. Spacing, we will give the value 2. And lastly, we need a color. We want white color. We are going to use the color definition of raylib for this, so we just type white in capitals. Let's run the game. Cool, the score title appeared in its position. Now let's add a rounded rectangle of light blue color to draw the score on. To draw this rectangle, we will use the drawRectangleRounded function. It takes 4 arguments, a rect, which is a rectangle structure that represents the position and size of the rectangle to be drawn. Roundness, which is a float value that represents the amount of rounding to be applied to the corners of the rectangle. Segments, which is a neat value that represents the number of line segments to be used in the approximation of the rounded corners. And color, which is a color structure that represents the color to be used for the rectangle. So in our main file, after we draw the scored text, let's create a rounded rectangle with the following values. Draw rectangle rounded, parentheses, curly brackets, 320, 55, 170, 60. This is the position and the size of the rectangle. Now we enter 0,3, 6, and lastly we need a color. As we said before, a color is a struct of 4 values. We need a light blue color for this game element. Let's declare this color in the colors.h file. extern const color light blue. Now that we work in the colors file, let's add a declaration for the dark blue color we are also using in the main.cpp file. Extern const color dark blue. Now let's give these colors values in the colors.cpp file. Const color light blue is equal to curly brackets 59, 85, 162, 255 and const color dark blue is equal to curly brackets 44, 44, 127, 255. Now, back in the main.cpp file, we have to include the colors.h file. Include colors.h. Now we can remove the dark blue color definition from here. We don't need it anymore. We can now use the light blue color inside the rounded rectangle function call. If we run the game now, we can see that a new rounded rectangle appears on the screen. Perfect. With the same procedure, we are going to create the title next and the rounded rectangle below it. For the title next, again we will use the same font. In the game loop, we duplicate this line. Shift plus Alt plus the down arrow key. We need to alter two things. The text is going to be next and the position on the screen is going to be 370, 175. Upon running the game again, you'll now see the newly added next text on the screen, which is a great addition to the user interface. The next step is to draw a rectangle below the title next to display the next shape. Again, we will create a rounded rectangle, so let's duplicate this line of code. We only need to change its position on the screen and its size. So inside the curly brackets here, we just enter these values. 320, 215, 170, 180. Perfect. If we run the game, we can see the new rectangle displayed. Now, the last thing we have to do is to display a game over message when the game is over and the basic UI elements will be ready. Let's duplicate this line to draw a game over text on the screen. We change the text to draw and the position on the screen. Quotes game over here, and for the position we enter 320, 450 here. Let's see if this works and then we will update our code to display this text only if the game is over. Beautiful, the game over message appears on the screen. We can implement a simple check in the game loop just before drawing the game over message to ensure that the message is only shown when the game is actually over. If parenthesis game.gameover curly brackets, and let's enter this line inside the curly brackets like this. That's it. Let's test the game. Beautiful. The game works fine and the game over message does not appear unless the game is over. When we press any key, the game restarts and the message disappears. With that, another step is now complete. Well done! We are now very close to completing the game. Keep up the good work. The next step is to add scoring to the game and display it on the screen. However, it is important to note that our version of the game is a simplified version of Tetris and does not include all the features of the original game for the sake of simplicity. Therefore, the scoring system will also be limited in our implementation. In our simplified version of Tetris, the player will earn points for clearing lines and moving the block down. Specifically, we can assign the following point values to different actions: 100 points for a single line clear, 300 points for a double line clear, 500 points for a triple line clear, and 1 point for each block moved down by the player. To implement this scoring system, we will need to add a score attribute to our game class. So let's open the game.h header file and add a public int variable to hold the score of the game. Int score. Now let's initialize it in the constructor in the game.cpp file. Score is equal to 0. Also, let's create a method that will be responsible for updating the score of the game. Again, in the game.h file, let's declare it. It will be a private method and let's name it void update score. We need to know two things, the number of lines cleared and the number of times the player moved a block down. So we need two arguments, int lines cleared, comma, int move down points. Let's work on the implementation now in the game.cpp file. Now we need a switch statement to award points according to how many lines the player has cleared. Switch, parenthesis, lines cleared, curly brackets, case 1, colon, score plus equals 100, break, case 2, colon, score plus equals 300, break, case 3, colon, score plus equals 500, break, default, break. Lastly, we need to add 1 point each time the player moves the block down. Score plus equals move down points. That's it, our method is ready. Let's call it. The first place where we need to call it is inside the lockBlock method, where we clear the rows using the clearFullRows method of the grid class. This method returns the number of rows cleared, so we can save this information in a variable. Let's call it rows cleared. Now we need to call the updateScore method and pass in this variable as an argument. UpdateScore, parenthesis, rows cleared, comma, 0. Now we need to increase the score when the player moves the block down. We have to do this in the handleInput method. When the user presses the down arrow key, we have to increase the score by 1. UpdateScore, parenthesis, 0, 1. Lastly, let's reset the score to 0 when we reset the game. In the reset method, we type score is equal to 0. Our score implementation is ready. Now, let's draw the score on the screen. This is trickier than it sounds. Let's go back to the main.cpp file. To print the score, we will just use the drawTextEx method just like before. Let's copy this line of code and paste it here. After drawing the large rounded rectangle, we want the score to be printed on top of it. Drawing the text is easy. The tricky part is how we are going to center it in this rectangle. The score text value won't have the same size all the time. As the score increases and requires more digits, the text width also increases. So, how are we going to center this text in a rectangle? Let's think about it for a moment. We have a rectangle which has a width of 170 pixels and a top left corner positioned at 320,55. To center the score text inside this rectangle, we must first measure the width of our score text. Let's say it is now 70 pixels. By subtracting the text width from the rectangle width, we are left with the empty space in the x-axis, 100 pixels in this case. To center the text, we must evenly distribute this space to the left and the right of the text by dividing the empty space by 2. So we need 50 pixels to the left and 50 pixels to the right. If we add 320 pixels to the resulting number, 50, we get the x-coordinate of the top left corner of the text object, which in our case is 370. We add 320 pixels because the top left corner of the rectangle is not positioned at the origin of our game window, but 320 pixels to the right. Let's do the same in code. First, let's convert the score, which is an int, into a character array. First, let's create that character array. Char score text brackets 10. Now we need to use the sprintf function to convert it. But to use this function, we first need to include a header file. At the top of our file, we type include IOStream. Now we are going to use the sprintf function. Sprintf parenthesis score text comma quotes %d comma game.score. Now the variable score text holds the text we want to print. Let's measure its width. We are going to use the measure text ex function of the raylib library. The measure text ex function takes in 4 arguments. A font, which is a font data type used to specify the font to be used for measuring the text. A text, which is the text that needs to be measured. A font size, which is a float data type representing the font size to be used for measuring the text, and spacing, which is also a float data type representing the additional spacing between characters in the text. The function returns a vector2 data type representing the width and the height of the text string in pixels, based on the provided font and font size. So let's use this function. Vector2 text size is equal to measure text ex parenthesis font, comma, score text, comma, 38, 2. We entered the font size and the spacing we will use to draw the score text. This function returns 2 values inside a vector2 struct, the width and the height of the text in pixels. We just need the width. We can access it like this, textSize.x. Let's modify the drawText function. We need to modify 2 things. The text is going to be score text. Now we need to modify the x and y position on the screen. The x position, as we said before, is 320 plus parenthesis 170, that's the width of the rectangle, minus textSize.x, that's the width of the text. And now we have to divide that by 2, /2. That's it. The x-coordinate is ready. The y-coordinate will be constant, 65. We are ready. Let's run the game. Amazing stuff. The score is now displayed on the screen. Each time I move a block down, the score increases. Let me show you what happens if I complete a row. Okay, the score increased by 100 points. Beautiful. Our scoring system works. Another step is now complete. We are now just 2 steps away from completing our Tetris game. The next step is to draw the next block on the screen. This step is relatively easy to implement thanks to the use of object-oriented programming principles in our game design. We will work on the block class. We already have a draw method that draws a block on the screen. We will reuse the same draw method. We need to draw the block but at another position, so we need an offset. So we will add 2 arguments to the method. So in the block.h file, let's modify the draw method declaration by adding offset x and offset y arguments. Int offset x, int offset y. Now let's go to the implementation of this method in the block.cpp file. We need to enter int offset x here and int offset y. Now, in this line where we create the rectangle to draw on the screen, we need to replace this +11 with offset x here and this +11 with offset y here. We don't need to hardcode this offset anymore since we have arguments for this. The draw method is ready. Let's now go to the game class. In the draw method, we draw the current block. We need to modify the method to add the offset x and offset y values. We add 11, 11 here. It is the hard-coded offset we removed from the draw method. Now all we have to do is to draw the next block on the screen. Next block dot draw, and let's enter 270, 270. Let's run the game. Beautiful. As you can see, the next block appeared on the top of the next rectangle. Cool. You can see that the block changes each time I place a block on the grid. But there is something that bothers me. The I block and the O block are not centered in the rectangle. I have to fix it. In the draw method, we have to check the ID of the next block before it is drawn on the screen. Let's use a switch statement. Switch, parenthesis, next block.id. Case 3, that's the I block. Give this block its own offset values. Next block.draw, parenthesis, 255,290. Break and case 4, that's the O block. Next block dot draw, parenthesis, 255,280 and break, default, all the other blocks work okay with the default offset. Next block dot draw, parenthesis, 270,270. That's it, our switch case is ready. It is not an elegant solution, but it works. Running the game again, we can now see that the blocks are appearing centered on the rectangle. This is a significant progress and another step towards completing our game. Before starting the work on the last step, which is to add music and sounds to the game, let's fix another thing that bothers me. Let's go to the game.h header file. As you can see here, we have many public methods and attributes that should be private. So, the getRandom block, the getAllBlocks, the moveBlockLeft and moveBlockRight methods can be declared as private. Let's do it. Also, the grid attribute should be private. Okay, let's run the game one more time to be sure that we didn't break anything. Perfect, our game works just like before. Now let's add sounds and music to the game. Sounds are important to a game as they provide feedback, create atmosphere, evoke emotions, and contribute to the identity of the game. Due to copyright reasons, I won't be using the original Tetris soundtrack for the game. Instead, I'll be using a theme created by my friend Spiros specifically for this video. The sound files are included in the GitHub repository of the game. You can find more amazing music by Spiros in a link provided in the video description. Now, in my game folder, I have created a new folder named Sounds and placed 3 sound files in it. One is named music.mp3, which contains the background music for our game, and the other 2 are rotate.mp3 and clear.mp3, which contain sound effects for rotation and clearing rows respectively. First, we need to start playing the background music when the game starts and ensure that the music loops continuously as long as the player is actively playing the game. We can do this either in the main file or in the game class. Let's implement it in the game class. So let's open the game.cpp file. Inside the constructor, we need to call the initAudioDevice function like this. This function initializes the audio device for playing sound in a game. This function sets up the audio system and prepares it for use in the game. Before closing our game, we need to close the audio device, so let's create a destructor for our game class. Game : tilde game, parenthesis, and curly brackets. Let's quickly declare it. Ctrl plus period and then enter. Now, back in our .cpp file, we have to close the audio device in the destructor. Close audio device. In the header file again, let's create 3 attributes. The first one is of type music and is going to be public. Music, music. The other 2 are of type sound and they are private. Sound, rotate, sound, and sound, clear sound. Cool, in the .cpp file now in the constructor, after we initialize the audio device, we need to load the music files. To load the background music, we use the loadMusicStream function. Music is equal to load music stream, parenthesis, quotes, sounds / music.mp3. We just enter the path to the music file. Before we close our game, we have to unload the music file. So in the destructor, we type unload music stream, parenthesis, music. Let's go back to the constructor. Now, to play the music, we just call the playMusicStream function. playMusicStream, parenthesis, music. This line of code plays the background music. We need one more line of code to make this work. We have to go to the main.cpp file and add this line into the main loop. Update music stream, parenthesis, game.music. Let's test it. Perfect. We can hear the music of the game. Now all we have to do is to add sounds for rotating a block and for clearing a row. Back to the game.cpp file, in the constructor, we need to load the remaining two sound files. That's easy. Rotate sound is equal to load sound, parenthesis, quotes, sounds slash rotate.mp3, and clear sound is equal to load sound, parenthesis, quotes, sounds slash clear.mp3. In the destructor, we have to unload the sound files. Unload sound, parenthesis, rotate sound, and unload sound, parenthesis, clear sound. All the sounds are now loaded and ready to play. All we have to do now is to call the play sound function with the sound we need to play as an argument. Let's work on the rotate sound first. We need to play the sound when we rotate the block. So, in the rotate block method of the game class, we add a call to the play method. Here we check if the rotation is not valid. If the rotation is valid, we need to play a sound. So we add else, curly brackets, play sound, parenthesis, rotate sound. Cool. Now we have to play the clear sound when we clear some rows. In the lock block method, we call the clear full rows method, which returns the number of rows cleared. If the number is greater than 0, we have to play the clear sound. So let's add a check. If, parenthesis, rows cleared greater than 0, curly brackets, play sound, parenthesis, clear sound. We can also add the update score method inside the if statement now that we have that check in place. The player will be awarded points only if he has cleared a row, so we don't need to call this method every time the user places a block. Believe it or not, with that change, our game is ready. Let's test it out. The music is playing, the sounds are playing, the score is updating, and in general, the game works as expected. Congratulations on finishing the Tetris tutorial. You worked really hard and learned a lot about making games. By creating this classic game, you improved your skills and gained valuable experience that will help you in future projects. Be proud of yourself and keep up the good work. To further your knowledge and continue learning, be sure to subscribe to our channel for more tutorials like this one. We will keep you updated with new and exciting projects that you can work on to enhance your skills. Thank you very much for watching this video. I'll see you next time.